Okay, great. Hello, everybody. I'm Tyson Ochsner, and I work here in the Department of Plant and Soil Sciences. My specialty area is soil physics. I'm an Oklahoma native, born and raised down in Tillman County, and then went to school here at OSU, grad studies at Iowa State, worked in Minnesota for USDA for 5 years, and have been back at OSU since 2008. So it's great to get a chance to visit with you all about the work that we're doing through the RAIN project. So I'll share my screen here and show you what I've got. So I want to talk about these cropland observation nodes that we are developing as part of the RAIN project. And first of all, to give credit where it's due to team members. Cole Diggins is a master's student here in Plant and Soil Sciences with us, and I think he's on the call today. Jerry Brown is another master's student here, and these two have done a lot of work to get these stations up and running. And then Andres Patrignani is a assistant professor at Kansas State University, and he's a lot of the brains behind the operation here. And so this is really a joint effort as we try to develop these new soil crop weather monitoring stations that are really, we're trying to optimize these, not for researchers, but for working farms. So with that said, I'll see if I can, So you already heard about the project. It is a USDA NEFA funded project, and we're focused sort of on the main winter wheat growing region in the U.S. And the overall goal of the project is to sustainably increase the productivity of rain-fed cropping systems in the southern Great Plains. It does not say dry land cropping systems, which is a term that we often use. And it's just to sort of recognize the fact that you see that area includes all the way up into eastern and northeastern Kansas and parts of eastern Oklahoma, where the term dry land wouldn't really apply. So these are rain-fed cropping systems. As we try to increase the productivity, we want to do that by increasing the precipitation use efficiency and the nitrogen use efficiency, and we'll talk about those a little bit more. We want to reduce yield losses to environmental stress and weed pressure. And we want to enhance soil health. So awesome for Dr. Lambert to kick us off on that topic. So there's the institutions involved: K-State, OSU, USDA Ag Research Service, and folks at the University of Maryland who play a really key role, really some of the experts on doing crop modeling and large-scale simulations in this area, along with some of the economic analyses. Okay, so just a question. I think this is supposed to be educational, and I imagine most folks on the call at some point have taken a class in soil fertility, perhaps. So I just wonder if you remember Liebig's law of the minimum. I wish we were in person. I could ask for a show of hands or something, but maybe you can type in the chat if you remember that or what that is. It's basically sort of a classical concept. It's often applied in soil fertility, and the idea that it's kind of like the picture of the barrel with one of the staves being lower than the other, so that the productivity or the yield can only go up to the level of the least limiting nutrient. And so that's been that's a kind of a model where you have sort of one factor limiting yield at a time. And so if you do remember that, maybe you ought to just forget it. I just say that really mostly as a joke, but increasingly as we understand more and more about how these systems work, we really, I think, more and more understand that it's not just typically just one factor that's limiting, but we have this idea of co-limitation. And here today, I'm really talking about sort of simultaneous or co-limitations of water and nitrogen in these rain-fed cropping systems. And so this figure on the right here is about as abstract as I'm going to get today. So, but it's kind of interesting. So Liebig's law, the minimum would be these sort of right angles shown here. So if we have two factors, resource A, maybe that's, nitrogen, resource B maybe is nitrogen, resource A, maybe that's water, or other two factors you might put in there. So if we're at this low level of resource B, Liebig's law of the minimum says it doesn't matter how much A you add, you're not going to get any increased yield. So the solid lines here represent a constant yield. Or if we look at this vertical line, we say, hey, if we're at this low level of A, resource A, then it doesn't matter how much more of B we add, we're not going to get any more yield. Well, as we learn more and more, it really looks like maybe this is an oversimplification of the process. Really, maybe it's more like these dashed lines where you do have some level of trade-offs between the resources, and you have what we would refer to as co-limitation. And it's interesting, the trade-offs, if you think about, as we were on the previous slide, about nitrogen use efficiency or water use efficiency, there are going to be some trade-offs between these use efficiencies when you have this kind of co-limitation. So imagine we're up here at this high level of resource B, maybe that's nitrogen. So we've got a lot of nitrogen, but our yield is still pretty low. It's yield level 1 here. So it's pretty low yield. We've got a lot of nitrogen available. And so our nitrogen use efficiency in this case would be pretty low. We could follow this line around and have the same yield way over here at a much lower level. If, let's say, if this was nitrogen, we could be at a much lower level of nitrogen, still achieve the same yield, but it took a lot of water to do it if this was water. And so then our water use efficiency is really low. And so you kind of see how there's trade-offs, and it might be tough or maybe not really possible to simultaneously maximize these use efficiencies. Basically, to kind of boil it down a little more, simplify it, you recognize that your crop is going to need nitrogen to benefit from those years when it gets extra water, when the precipitation is good, when the soil moisture is good, you're likely to need extra nitrogen for your crop. Likewise, if you apply the extra nitrogen, you're probably going to need water to achieve the full benefit. So that's kind of the concept here. And then, of course, that immediately brings up the question, well, I mean, you might know how much nitrogen that you apply, or you probably will know, but how can you know how much water is currently available or you might expect to be available in the future? Well, again, these are rain-fed crops. So when we talk about how much water is available, it's not irrigation or precipitation that we're thinking about. It's how much water is in the soil. That's what's available to these crops. In Oklahoma, where would you go to find out how much water is available for your crops? How much water is in the soil? Well, you might go to the Oklahoma Mesonet, which is a fantastic resource that I'm sure many of you use regularly. And you could scroll through the options there, and you could find a map like this one, which is the one-day average 16-inch % plant available water. That's basically in the top 0 to 16 inches of the soil, how much of that available water capacity is currently filled with water. And this is a map from November 22nd, so a couple of days ago. And a lot of the states right up around 100%. It's those soils are full, at least in that layer. Some of the states, though, way out west in the Panhandle and over here in part of Southwest Oklahoma, still pretty dry in places. So you might think about going there and finding some estimate of, well, how much water is available for your crop. And I would say that's good. So that's a good resource. But, it's got some issues. So if I'm looking at this kind of a green shaded area, how do I know exactly where's my field in this, or the particular field maybe that I'm consulting on or interested in. It's not very descriptive here spatially, so that's maybe a limitation. Well, okay, so we have something else. So this is another source of soil moisture information for Oklahoma. If you go to soilmoisture.okstate.edu, or this is actually linked from the Mesonet these days, and there you can get a lot more detailed map of the soil moisture conditions across the state. These are at a half-mile resolution, so half-mile by half-mile roughly. It's about a quarter of a section. And so we can start to sort of zoom in and get, much more site-specific estimates of the soil water content that we have for these three depths. There's 5, 25, and 60 centimeter depths. And you can click back through different days and different months to see how it's changed over time. So that's a good resource. And you can actually go, there's a link I've included here. If you go to that link, you can use the little map to select any point within the state, more or less, and download 5 years of daily soil moisture estimates for that specific point. And so that's a pretty cool feature that might be useful to you in some ways. You try to think about how much water is available for my crop. So I would say that's better in some ways. But here's the big problem with both of the two things that I've shown you. They're all based on the measurements from the Oklahoma Mesonet, and all of those measurements are taken under grassland vegetation. None of those measurements are taken in cropland. So we know that at times there can be really substantial differences between the soil moisture conditions in your cropland versus what's in the grassland, even in that adjacent area, right? And I'm sure you've seen that at the end of the summer, your ground in your pastures might be really dry, but maybe your wheat fields that have been fallow over the summer have recharged some of their soil moisture, and you can see that difference. So that's a big problem. So maybe the best way is if we had monitoring of soil moisture conditions actually in the cropland. And so that's what a big part of what we're working to do here. So this is a photograph of Jerry and one of our CRONOS stations. This is station OK003, which you'll see some data from it as we go forward here. So the goal of these CRONOS stations is to provide portable in-field cropland monitoring stations. So there's nothing in the ground. We're measuring soil moisture, but there's nothing that you have to bury or put in the ground. So I'll explain that. For measuring soil moisture, we use a cosmic ray neutron detector, and that's inside this white box here. And so yeah, cosmic rays. It's just as far out as it sounds, and I'll explain a little bit how that works. For monitoring the crop, we're using a trail camera, a game camera that's equipped with cellular communications and downward facing to take images of the crop multiple times a day. And then we have up here on the top a compact all-in-one weather station that gives us a lot of really valuable data. And again, all of this is delivered wirelessly. And so we're trying to put all the pieces together and optimize the design of these kind of stations to provide another tool that growers can use in their management, in their decision making. So just a little background on this cosmic ray neutron method that we're using to measure soil moisture. Okay, so starts in outer space. So in the galaxy around us, there are these cosmic rays. There, if you remember your chemistry, protons, neutrons, electrons, these are high energy protons mainly that are coming in to Earth from outer space. And as they come in, those protons are colliding with atoms in the atmosphere. And if they hit the nucleus of an atom, they may cause that atom to emit a neutron that's moving at a high rate of speed. And so it's called a fast neutron. And as those fast neutrons come down, they may hit another atom in the atmosphere and cause it to release a fast neutron as well. So you end up like this cascade of fast neutrons coming down to the ground surface. And this is happening all the time. It's happening right now. We just can't sense or detect those with our 5 senses, but it's happening. And so these neutrons are coming down. Some of them are penetrating into the soil. That's shown here in figure B. And they bounce around in the soil, and they may come back out and move around again up in the atmosphere. So they can kind of go in and out between the ground and the atmosphere as they bounce off things. The one thing that's really good at slowing down a fast neutron is a hydrogen atom, because it has the same mass, the same atomic mass. And so the more hydrogen we have, or basically the more water we have in the soil, the fewer of these fast neutrons we're going to see. As the soil moisture goes up, we detect fewer of these fast neutrons here right above the ground surface. And so this is a calibration curve shown in this figure, where we have that neutron detector in the white box. We detect, how many neutrons, we count how many neutrons we detect in a given time interval. So that's the counts per minute or counts per hour shown here. And then we can relate that to a soil water content through a calibration curve like this one. And the cool thing about this method, number one, other than that nothing is in the ground, is great. But number two, it's sensitive to a large area, because those neutrons are moving so fast, they explore a large area around the detector, can be out to maybe 200 yards in all directions around the detector. So it's really a field scale type measurement. Okay, now with the crop condition, we again use digital images, trail camera. Maybe you're checking yours for deer these days. But we typically are taking 5 downward facing photos per day. And each of those photos gets analyzed using our Canopeo algorithm to measure the percent green canopy cover. And so for this sorghum crop there, you can see we're at 41% canopy cover in that particular photo. And of course, you know that the canopy cover, the amount of green canopy cover that you have it's number one, it's going to be related to the water use and can help us estimate the crop water use. It's going to be related to the biomass of that crop. And it's going to be related pretty strongly to the NDVI, which is interesting, because as you know, Dr. Arnell, Dr. Ron, and others have been developing lots of great ways to use NDVI information for nitrogen management. So I think there's really some potential for us to explore here with these data. And this is something that hasn't been widely done yet within agriculture. So it's a lot that we can learn about how to monitor our crops this way. The weather conditions come from this really cool all-in-one weather station. We didn't design this, but we're using it and liking it really well so far. It has no moving parts, so that's a great feature in terms of longevity. It gives you lots of the key variables that you might want. Of course, rainfall, solar radiation, air temperature, relative humidity, wind speed and direction, barometric pressure. All of these things come from this one little compact sensor. And we've put these out and compared them to some Mesonet stations, sort of as a ground truth. And here's a couple plots showing average daily temperature and daily precipitation. And it's looking pretty good in terms of how it compares with the more robust, larger Oklahoma Mesonet stations. So that's how we're monitoring the weather. So I want to show you some of the data, and this is definitely still a work in progress. The soil moisture data, because of the way that the particle physics worked, the Neutron data are just pretty noisy, and you can see that here. And so we'll have to continue to work out a bit better practices on our filtering those data to get a nice sort of a continuous estimate of the soil moisture conditions for a field. But this is from Chrono Station number 2, OK002, which is near Frederick, Oklahoma. And this was in a cotton field over the past summer. And you certainly can see how the water content of the soil is going up and down over time, responding to rainfall events, et cetera. This still needs some work to be able to get this calibrated and validated, and then also improve the noise levels here. But it's coming along on the soil moisture data. The crop data, I'll just show you an example of that. The images give us really nice sensitivity. They probably are more sensitive maybe than our eyes might be in detecting the crop growth and development. So here's an example from a station, OK003, which is near Bremen, Oklahoma, and just really clearly shows the early growth of this year's winter wheat crop. And so this is not so long after planting. This field had been in sorghum, as I showed you before, and after the sorghum harvest, then no-till planted into wheat. And on November 7th, you can sort of maybe just barely make out the wheat beginning to emerge and come up there. And then if we go to November 23rd, which was yesterday, you can see we've repositioned the camera, but you can see the development of the crop. You can tell it's made some progress, but once you take that sequence of images and run it through Canopeo, you can really see day by day the growth of the crop. And so we went from, on the November 7th, we're down around 4% green canopy cover, and as of yesterday, we're up to almost 10%, right at 10% green canopy cover. So you can really track the progress of these crops and potentially give you sort of an early indication when that growth starts to lag. So we're excited about following these stations. We have 3 stations in winter wheat across the state we'll be tracking throughout this growing season. The weather data, I just want to show you a quick example of that. This figure shows 2 of the variables. Again, this is from station number 3, which is near Bremen. It goes from November 7th through the 14th, so a week of data here. And the blue line is the solar radiation. So if we have a nice clear sky kind of day, we should see a smooth, increase in the solar radiation reaching a peak when the sun is at its highest point overhead, and dropping back down and being 0 during the nighttime. So you can see that first day, nice, probably cloud-free day for the most part. You can see, the effects of clouds pass over. You see little dips in the solar radiation, or you see, like on November the 9th, I don't remember that day, but obviously was a real cloudy day. Our solar radiation was very low. Temperature was nice and warm. The red line here is the air temperature. So sort of a warm, cloudy day. And then we get kind of a sequence of sort of 1, 2, 3, look like really clear days where you got that nice, smooth progression of the solar radiation throughout the day. Well, as you have those really clear days and clear nights, this time of year, you know that our nighttime temperature is going to be dropping lower and lower. And sure enough, you can see after the 3rd day like that, we got a couple degrees below the freezing point here. So just an example of what some of the weather data look like coming from these stations. Seems to be really good quality data that will be useful, I think, for a variety of different purposes. So now the key, of course, is to get that data back to our growers in a timely manner. And so we've developed a prototype website. I'm showing you a little screenshot from the website here where it'll display the crop images. Here's an image. This is from station number 2 down in Tillman County. And so you can see the wheat here and the canopy cover measured over here. This one's at 35% canopy cover right now. You see the last couple of days of air temperature data. And another nice plot here is the wind direction, which is shown down here in the circle, and the wind speed, maximum gust speed in meters per second. So these and other types of data are available on the website because we've got that data coming in by cellular modem. We've got an FTP server that receives those, working out computer code that will automatically process those data and post them to the web. And so we have 3 stations in Oklahoma that are currently up and running and 2 in Kansas. So we're building out this network. Just some next steps before we close. Of course, soil moisture, we still need to work out and finalize our calibrations and then removing the noise from those signals. We're working on improvements to the Neutron detector, working with another private company to develop lower cost Neutron detectors with similar resolution. Switching to also a lower cost data logger, working with a separate company. Working out some details in our power systems and our tripod, our leveling system. Lots of stuff here, especially related to the tripod, to figure out how do we make this work well for a producer so that it's not too cumbersome in terms of their field operations and being able to move these around. Ultimately, we're aiming to develop and deliver in-season crop forecast to inform management decisions or increase productivity, which goes back to the objective of the whole project. And just a little sneak peek of what something like that might look like. Here's a forecast of soil water availability. It's a, I guess, a historical forecast because we were forecasting a past year, a wheat growing season near Stillwater that started in the winter of 2012 and went over into the spring of 2013. And so we have the red dots, which are some observations, and the red line, which is our model. And then we have a forecast date here of March 1st. So if we only knew the conditions up until March 1st, and we run the model going forward with historical weather scenarios, then we get this sort of envelope, widening envelope of possibilities for the future. So the gray shaded region kind of represents our forecast, and the red line in the middle is sort of the average or the median value of that forecast. So if we can start to forecast out the water availability, then you can imagine how that might link into forecasting out the potential crop yields and how that might then influence what you might want to do with maybe late mid-season nutrient management, pesticide applications, or maybe it's marketing decisions. So that's some of the direction we want to pursue moving forward. So anyway, thanks to Dr. Arnell for organizing the session and also hosting the first Chrono Station in Oklahoma. Thanks to our cooperating growers and our funding agencies. And I'll just invite you, if you're interested in any of this, please get in touch. There's my email address. We've already seen the website for the Rainfed Ag project. There's a few others here. I'll just mention maybe the Canopeo app. If you're not currently using that or haven't been using it, that's a free app for measuring canopy cover with your smartphone. So you can use that. And just a little bit more broadly, we're part of an initiative called the Rural Renewal Initiative, which is working on not only agriculture, but a variety of different issues impacting rural communities. And so if you're interested in that, you can check out our efforts at ruralrenewal.okstate.edu. And with that, I will stop sharing my screen and thank you for your attention.
Thank you, Dr. Ochsner. That was fun. Does anybody have any questions for Dr. Ochsner at this time?
Looks like maybe in the chat. Oh, no, it's okay. So somebody's asking where are the sites in Kansas? Okay. Yeah, we'll have to ask Andres. I don't know the exact locations, or maybe Ignacio, Dr. Ciampiti can maybe fill us in on that later. I think one is close to Manhattan, and I don't remember where the other one is.
Gotcha. The other one was in Hutchinson, just.
Oh, okay. Yeah.